Okay, yes, it's working. So it's great to be here in Serbia. I'm quite a big fan of Serbia. I've been working with Serbian engineers for quite a long time, and now at Foursquare I've been part of setting up an office here in Serbia. So it's just natural that we kind of engage with the technical community here. I'm going to talk about Vis.gl, and so this is about big data visualization, and in particular geospatial visualization and compute. And so maybe the thing that's a little bit unique about what my approach and approach of Vis.gl is that we do this on the front end. So, most geospatial analytics is arguably done on the back end. And the kind of core idea is that today in the client, you usually have a very powerful GPU. So whether it's on a desktop or even in an iPhone, you may have a much more powerful GPU than you have on the back end. And the GPU, maybe we traditionally think about it as something where you render a scene graph with a lot of draw call for the different objects in a game. But if you look at the architecture of a GPU, it's really a binary columnar table processor that's able to process rows in parallel, hundreds or thousands of rows in parallel. So it's an incredibly powerful tool if you can use it right to work on big data. You can get the big data into your browser, and then you can make computations on it, and then you can visualize it. Over the years, we've built up an entire ecosystem of frameworks and applications. This is the current state of Vis.gl. These frameworks are all independent. They're composable. They can be used with other frameworks and independently in applications. But of course, they're all created to work seamlessly together with each other. They are JavaScript frameworks, or more correctly, now TypeScript frameworks. We have the core stack with deck.gl, which maybe is the crown jewel of the offering, and a number of supporting frameworks. There's also some incredible add-on frameworks that's been developed by different contributors. That we're going to take a quick look at those. And one thing that you typically want when you do geospatial visualizations is that you want to show them in the context of a base map. And so there are many options to choose from. They can be quite hard to integrate. They have different APIs, and they typically are pure JS, and they don't work well with, for instance, React. So we have very mature wrappers for those. We also have entire applications that are open source. So kepler.gl, which I unfortunately don't have time to go into much, is an open source application that uses the power of this framework for exploratory big data analysis. One thing that I think stands out also is that we have Python bindings, so that you can use the power of Vis.gl directly in a notebook, for instance. So if you're a data scientist using PyDeck, you can create a map inside of a cell, and you do the same type of visualizations and analytics that you would do in your web application. There's a lot to cover here, more than I can possibly fit into this talk. Some of you may not be familiar with the suite, and so I'm going to briefly talk about some of the frameworks. So deck.gl is GPU-powered geospatial analytics and visualization. The core design notes, as I mentioned, it's modern, TypeScript is modules, all the good stuff that you want. It's GPU-powered, big data, all centered around efficiently as possible handling big data. It is reactive in the sense that You can work with it in a functional way, and it works seamlessly with React, though it does not depend on React. It has React bindings if you want to really have a convenient integration, but you can use it with other frameworks. And again, it has many bindings. There is a pure JS version, there's a scripting for ease of use. There's the React bindings. We also have a JSON version of it. You can create JSON descriptions of your layers. There's Python bindings, even R bindings are developed independently. Now, at the core of the offering is a catalog of visual layers. And so these, you can think about each of these layers as a really optimized GPU, a set of GPU shaders and associated code that generates some visual effect. And the way they work is that every layer takes a data property. And data property is a table. You provide a few accessors describing which of the columns in the table should map to different things, and some styling. And then this is all rendered on the GPU. So you see here there's arc layers, there's column layers, you have this kind of network. There is just a variety of layers, and they can be composed to create very advanced and unique effects. And there is also the ability to create custom layers if you know a little bit about shader programming. And these layers are very performant. They can typically handle at least 1 million rows of data directly on the client. And we're kind of talking about the basics, but we have views and transition systems. So here's an example of a multi-view deck.gl application. It has 9 views, and each one represents presumably a city where this company is operating. And so you can put the cities next to each other in this case, and you can do easy visual comparison for an operator and see what's going on. Or you can visualize the same data set in different ways in different views. And animations are built in, and they're GPU-driven animations. So if you change your data or your view, then you can easily configure it so that they interpolate, so that you get a seamless transition. You can see here as the camera moves seamlessly, that doesn't require the application to constantly feed new states, but is automatically interpolated on the GPU. And even the data as it moves around can be handled automatically. And there's a variety of first-person views. This is a globe view. The beauty of it, you have an application, you've already developed it for deck.gl in a flat or perspective mode. And now if you want to show a globe view version, then you just add a globe view to your application, and it just works. And of course, temporal animations, which is one of the core features, also work really well. Here you can see global weather unfolding. When you work with really big data, at some point you're always going to get to a situation where the data, no matter how much you optimize it, doesn't fit into the browser. So one of the kind of traditional ideas in geospatial is to tile the data. And there is quite a variety of different ways to tile. 20 years ago, we had these bitmap tiles, image tiles, where maps were divided in a pyramid of images, and depending on when you zoomed in, you loaded images with more resolution. 10 years ago, maybe Mapbox launched Mapbox vector tiles, and that gave us really sharp graphics. Recently, there has been a development on 3D tiles, and so today you can take photorealistic 3D data of cities, you can see it here, and these can be basically of unlimited size, but you can load them interactively directly into the browser. There's a certain amount of work required to create a good client for loading tiles, but there's a bunch of tricky corner cases, and so these are quite mature. They handle if a feature is divided over 2 different tiles and you highlight it, you want both the pieces of that feature or building or what it is, whatever it is, right, to be highlighted. And so cross-tile highlighting, offsetting these tiles with terrain and so on, right? There's a lot of work that's gone into these layers. Aggregation. So aggregation is a very powerful technique in in geospatial data analysis. And so if you think about, let's say that you have a lot of events, and this top blue thing that we're watching here, it's actually I believe, traffic accidents in England. Now, every traffic accident has a longitude and a latitude associated with it. Now, if you plot those just as points, you risk having a lot of points that are in more or less the same spot, and you can't really tell. It just looks like one point because they draw on top of each other. So what you do typically is that you aggregate into some kind of cell structure, and then you count the number of points that end up in that particular cell, and then you visualize that point with the more intense color, or even with an elevation, as you can see here. And so in the power of deck.gl here is that it does this aggregation on the GPU. The aggregation can be quite heavy on the CPU, and so we can do re-aggregation every frame in 60 frames per second. And so we can animate, you can see as the data changes, or maybe as the viewport moves, and you can have your cell sizes and so on dependent on the viewport. And you can see the aggregation happening basically as the user zooms in. So this is a nice feature. There's so much more to say about deck.gl, but that gives you a taste. Now, moving on to companion framework, loaders.gl. So getting this data into deck.gl or into your application can be quite challenging. A lot of the innovation in geospatial analytics happens on the file format level, and it's been going on for many years, and it's continuing even today with a lot of new exciting formats coming out of standardization and so on right now. And so loaders.gl is an expanding catalog of loaders. It has a fully typed interface, and it, with a lot of good features, worker threads, node support. The loaded data is optimized into typed arrays so that it can be uploaded directly to the GPU. You can build composite loaders and so on and so forth. But it offers loaders in a variety of categories, and these loaders load data into basically the same, if they're geospatial tables or and so on, and you can expect the data to come back to be very similar, and it makes it very easy to work with. You can support multiple formats with a low effort, and that's basically what we're saying here. And of course, while you can use these loaders independently and just use them in any application, deck.gl layers are written so that they can directly accept the output of loaders.gl without any further processing. It makes it very, very easy to add format support for some new advanced geospatial data format to your application. One of the kind of highlights of loaders.gl is that there has been a particular big investment, even from the industry, has been funding development in open source for the new massive 3D data formats, 3D tiles, and I3S. And so the implementation in loaders.gl is very mature, and there's a lot of work on the performance of the loading, the accuracy. We also support the latest specifications. They're actively being developed, 3D tiles v1, 1.1, and so on. I3S 1.8 plus. New archive formats are coming out, making it easier to work with these. And we also have a very advanced command line tool for format conversion. So if you think that you're stuck in one of these formats, that's no longer the case, you can easily migrate your data. And of course, it's not just about loading the data for visualization. You get full access to the metadata and the structural information. You can select buildings. You can get all the metadata on each object. You can do analytics. You could, for instance, color. Let's say that you have a set of buildings, and you can identify the different buildings. And the different buildings may have an age or metrics like age or elevation or energy efficiency or closeness to a park or whatnot. And then you can color them differently based on various attributes. So there's quite a few options for doing visual analytics and actual analytics. I won't go too much into the details unless you're using loaders.gl. We have been putting a lot of work into the new version. We have some of the new cloud native geospatial formats, PM tiles and geopoke are coming here that we're very excited about. Right, so now you have these visualizations, and we talked about you really want to have, you often want to have a kind of geospatial context. You want to have a base map underneath your visualization so that people can see immediately where these things are happening, you know, on the Earth. We have a wide variety of integrations. We have Google Map, MapLibre, Mapbox.gl, ArcGIS. I think there's an independent leaflet integration. But in particular, we have very strong support for Mapbox and now MapLibre. And this is one of the most used frameworks in the suite, used by many applications that don't use deck.gl. And recently, Google has joined and funded the development of a similar React wrapper for Google Maps. And if you followed Google Maps, you may know that they recently relaunched Google Maps that had grown quite stale, and now they have a full, you know, very impressive WebGL-based renderer. And so you can bring in these, you know, very impressive new maps into your applications very easily. We talked about we mentioned that there were add-on frameworks. So these are, you know, some very talented individuals and groups that have done very specific things that sit on top of deck.gl. And so FlowMap.gl is a framework that takes a data set that basically contains origins and destinations. And so, you know, you have 1 million maybe things that are moving. Maybe it's cars or people or whatever that's moving through a city, let's say. Now, it's very hard in that noisy picture to get an understanding of where are the flows really going, where are the, you know, is it just like a random, people are moving all over the place at random, or are there major flows? And so this layer automatically extracts the big flows out of that noisy data, and then it does it in a way so that it depends on zoom, and if you zoom in, it kind of re-aggregates and gives you finer and finer detail. So it can be very powerful for specific types of analysis. Another add-on framework that is, you know, really useful is Nebula. It's when you want to edit data, there's usually a number of solutions for that written in JavaScript and so on. But when the data sets get really big, a GeoJSON with 100,000 features or something like that, they typically get performance challenged. And so this is a GPU-powered editing framework that allows you to edit really big data sets. And of course, it works, integrates seamlessly. It's all rendered in WebGL. And so the rendering of these, you know, of the structure under editing, you know, happens on the GPU and you know, it interacts perfectly with the rest of the visualization. It also, as you can see here on the side, it has a wide range of composable edit modes, so you can very much customize it to fit your application needs. Another amazing framework is Hubble. It's client-side video generation, and so it handles all the tricky cases that you need to consider when rendering to video rather than visualizing. So for instance, when you render it to video, when we visualize, it's okay if there's still some tiles loading, they will soon pop in, and the user is okay with that. But when we render video, we want it to be perfect, and so we have to synchronize each frame and make sure that everything is loaded, and then before we then capture that frame. It comes with animation APIs, and it has a save function to a growing list of formats. There's GIF, MP4, WebM, and we're looking at additional formats. And well, it's framework agnostic, as most of these frameworks are. Of course, it has seamless integration with Deck. Well, so obviously I didn't build all of this myself. There is a very strong and vibrant community behind it. about a year ago, we joined the OpenJS Foundation, and we formed a new collaboration space. So if you're familiar with the OpenJS Foundation, they have many of the big JavaScript tools that we all use and love. Node.js, for instance, is maybe the biggest member of that foundation. But now that we have joined here, we have the start of a visualization space within there, and we're hoping, obviously, that other frameworks who may be considering to go not only open source, but actually want to go to open governance, would like to join us. And so, and there is possible to join the community. This is openvisualization.org. And if you click this join the community, there are Slack links and links to meetings where you can zoom in and talk to us and so on. And it's quite a wide group of companies. Maybe these are the highlights, not at all exclusive. And so, as you can see, it's really a who's who of geospatial and software companies that are collaborating here. We just had our second collaborator summit. This was in Foursquare's offices in New York, and you have here, a very awesome cast. We have the representatives from Microsoft. We have the CTO from Kato. We have NVIDIA. We have Google's director of maps is here in the first row. Amazon was there, and people were flying into New York to attend. So this was really exciting and showed the kind of energy that we have in the community. Giving a little sense of where we're at. We're getting close to 200,000 downloads per week for deck.gl. React Map.gl is at almost 350,000. We had 27 community meetings over the last year. We had over 107 different unique users contributing PRs, and obviously a lot of users opening issues. It's being used quite widely across the industry. Now, take a little break here, but this is, I'm going to give you just some highlights what happened in the last year, just to show you the pace of development and innovation that's going on right now. So we, as you could see, we had for multiple years, we've been working on this support for massive 3D data. We were immediately convinced about the, the potential of these technologies. The problem is that there hasn't really been easily accessible data, and so what happened fairly recently is that Google launched their photorealistic 3D tiles. So we had to do a little bit of work to get our tile 3D layer to work with the way they manage tokens and other things. But today you can just go to Google, get a token, input it into the tile 3D layer together with a URL, and you're up and running, and you have this type of visual data available for 2,000 plus cities around the world, and it is just amazing the visual impact it has. This is, and what we obviously already had is we have data-driven rendering, and so we talked about that before. Here we have the buildings then being colored. In this case, I believe it's based on their distance from the closest park. So. And another feature, something we wanted for a long time, was the ability to combine flat data with terrain. And so when you have a terrain, if you naively do this in 3D, well, all the flat data will render below, and then the mountains will sit on top of and hide everything. And most examples you see from these type of kind of frameworks are often like in a city by the coast, like San Francisco and New York, where basically the buildings are at sea level. But if you go inland, you can often be 1,000 meters above sea level, and nothing really works well. And so now we have a terrain extension that basically can lift all your visualizations on top of the terrain. It works in two modes. We have a drape mode, so we can render things into textures that we drape over the terrain. Or we have an offset mode, so if you have more of a 3D structure, we can have all the geometries offset by the terrain elevation at that particular point. And of course, everything happens on the GPU. When working with base maps in particular, one of the problems is that there are so many labels. And so as you zoom in, obviously well, if you zoom out, the entire screen will be covered by overlapping labels. And sorting those labels can be quite tedious to do on the CPU. So what we've done is we've implemented a collision filter that you can add to any layer. And on the GPU, it basically does an overlap check and filters out and selects the most prioritized label. And so this makes it very easy to, with a big data set that's very crowded, you can add like a priority function or a priority column, and then you can automatically on the GPU have deck.gl, so to speak, declutter the visuals. And now our text layer auto-selects the prioritized labels. And typically here it would be city names based on population, right? Another thing that we've also wanted to do for a long time, once you do a visualization, you may want to clip it. You may say that it should only be shown within a ring or a rectangle or some more complex area, maybe representing a zip code or census block group or something like that. Now we have a very generic clipping mechanism that where you can render one layer and you store it as a mask, and then you can render other layers and reference to that mask, and then basically they get clipped on the GPU. So you have basically any layer that's in the deck.gl catalog can become a mask, and the possibilities here are almost limitless. And well, there's a lot of other nice things. The MapLibre integration now with Mapbox going more commercial source and no longer being open source has been a big deal for the community. And we have support for some new formats like services like WMS and so on, deeper integration with Mapbox. So, well, what's coming next? In version 9 that we're heading up towards now, the big item is Web GPU. So this is embracing the next era. WebGL is getting 25, 30 years old. And Web GPU is basically a web API that exposes the most modern web GPU APIs like Metal and D3D12 and Vulkan and so on. And it's starting to become available. It's been available since May in Chrome and coming slowly in other browsers. And it will bring better performance. It is much less, there's much less validation going on the CPU. You build more immutable objects, and there's also support for more advanced ways of rendering that GPUs support today. There's particularly exciting is that there now are dedicated compute shaders, and so you can work much more freely with memory in the GPU than you could before, and that opens up for many new types of applications. Yeah, it's a modern API. We can also do more robust context sharing. Sharing the WebGL context between, for instance, Mapbox and deck.gl has been very tricky because WebGL uses a lot of global state, and if one of the frameworks forgets to clear some global state, they can kind of pollute each other and can cause very hard to debug issues, because Web GPU doesn't have global state. It makes this much more robust. I guess time-wise, I don't know if I have time to go into the details of the API changes, but what we're also working with is interoperability with other GPU solutions. And so we're working with TensorFlow. We already have examples up on this. TensorFlow JS has a big library of algorithms running on the GPU. And of course, many of them machine learning specific, but many of them also quite generic. And the beauty is that the computation is done on the GPU, so we don't have to take it back to the CPU and then back to the GPU, which is really the performance killer in this type of contests. And we're also working with NVIDIA, who's participating in, and they've been building CUDA integrations. So if you're using the backend and you have access to CUDA, which is NVIDIA's state-of-the-art GPU APIs, you can also run deck.gl on the backend. And the kind of performance you get out of that is absolutely crazy. So another thing that's coming is maybe less GPU-centric, but very important for users. So when you build these applications, you typically want to have some widgets associated with it. And now there's going to be these widgets that comes out of the box with deck.gl, very easy to add compasses and full-scale controls. And there is a very long list of widgets that are coming. These are some design concepts. The widgets automatically get notified when the view changes, which layers, it knows which layers are in deck.gl, which views, and so on. And so they can be quite powerful. Here are even more advanced widgets that would actually look into the data and be able to, so with just a line of code, you'll be able to add very powerful widgets to your application. And as you can see here, you just add a couple of widgets as a prop to deck.gl. All right. There's theming, of course. So this is being designed carefully to be, using CSS variables and other things, so that it will be, easy to configure. There'll be available themes, the dark and light, I suppose, and then you'll be able to do your custom. Loaders.gl v5 then, what's going to happen there? Well, there is a big movement in the geospatial data industry that's right now that's very exciting, and it's this family or group of data formats that are called cloud native. And cloud native really means that they can be used in a serverless way. So you, for instance, if you look at PM tiles, instead of creating a huge hierarchy of tiles that need to be served, it puts all the tiles in one big archive, and it puts metadata in the beginning, and you read the metadata. Once you've done that, you read it with a range request. You don't load the entire gigabyte or terabyte file into memory. You read with a HTTP range request the first metadata, and then you have all the information to tell you where the different tiles are, and then you can do additional range requests and read those. So you can just put a huge gigabyte or terabyte sized PM tiles file up on an S3 bucket and make it public, and then applications like deck.gl can start reading from it. GeoArrow and GeoParquet are kind of considered part of this. I've been part of the standardization of GeoParquet, so if you're using Parquet, you can now add geospatial metadata, and you can visualize those things directly in deck.gl. The cloud-optimized GeoTIFFs is similar for raster data. Services. So the kind of older generation of data formats, many of them require services. There is a special API for querying them. If they're older, it may be XML-based, which is a little bit hard to work with in JavaScript, or if they're newer, they may be JSON-based. So we're providing a library of services. Certainly for the OGC, the Open Geospatial Consortium, we already have the WMS Web Map service, and working on a few more, and there's also opportunities to add ArcGIS service support and so on. And that comes to the kind of end of what I'm going to tell you about the open source. So everything you've seen till today It's all open, it's all free, it's open governance, it's owned by the OpenJS Foundation, the Linux Foundation. It's not owned by a single company. It can never become, there can never be a company that says that we're going to take this proprietary now, or it's really owned by the community, by us. And so, but of course, on top of that, to fund this, all this good work, there has to be something that pays for it. I'm personally building commercial offerings on top of this now at Foursquare. But many other companies are building both internal applications and also commercial products on top of this. So the product I work on is Foursquare Studio. And so I think I can honestly call this an open core product. So everything you see here is part of the open core. When we add a new file format to Foursquare Studio, we develop it in loaders.gl as an open source and everyone can use it. But then we package it. You know, we say it's the power of Vis.gl ecosystem at your fingertips, but then it's combined with a geospatial SaaS platform and SDKs, and of course Foursquare's world-class geospatial data. And so we have free accounts, and it's kind of a freemium service. So if you want to play with it, you can sign up at studio.foursquare.com, or you can go to our open source application, kepler.gl, which has a subset of that functionality, but you know, obviously it's not backed by cloud or commercial data. So really invite you to look at our frameworks or try out kepler.gl, or of course, we'd love it if you gave Foursquare Studio a spin. So, and this is a video. It's kind of been sped up quite a bit, and it shows how an experienced user of Foursquare Studio works with a data set. I think this case it's a New York taxi data set, a rather famous data sets in some circles. And so you can see how different layers and so on are being used. So here, the data set is being loaded, and you know, some initial point layers being there, the styles are being experimented with, and then now animations are being added, first as trails, and then actual 3D models for cars are being put in place, and then you know, animate like this, changing base maps, adding charts, and then adding data, injecting additional data, and enriching it from the Foursquare for the data catalog. And then now you can see how we're adding the 3D tiles. So now we have a real 3D landscape in which you can see relating time playback. You can see shadows being cast and move over. You can visually see the time of day. It's astronomically correct shadows. And then now we're using annotations here to highlight the different areas that we want the viewer to consider. And now we're adding post-processing effect, like a Photoshop for map makers, and you can add halftone and tilt shift and other things to create a map that then has dramatic impact, that is really beautiful, and that tells the story about the data, that the insights that you arrived to at it in a really powerful way. So, yes, that's all I had, and I invite you to come and join the community. There's many ways to do so.